So, hi everybody. The topic for this session is SAI for VOQ system, and it will be 15 minutes, followed by Sonic for VOQ system. So we will cover the two parts, hopefully in 30 minutes, a little bit short, but we will do our best. So I am Israel Malik, a Broadcom fellow. I joined the Dune Network, a small startup at the time, in 2004. The company was then had the best in the market TM and fabric technology, and my mission was to add the packet processing technology. So I established a group, and 16 years later, we are in about our 8th generation of what we call the DNX product line. The recent device that we shipped is Jericho 2C+, a 14.4 tera device with deep buffer, large-scale databases, going into all the major service providers and cloud providers, the biggest providers in the world. This is, I believe, the leading merchant silicon switch router device out there. So today we will cover SAI for VOQ system. And to do that, I will start by explaining why VOQ system is different than basic switch and how. Then I will explain what are the addition and changes needed in SAI to support VOQ system. And finally, we will go over a short status of what have been done and what are the coming milestones looking ahead. So to explain a VOQ system, I will start with a basic switch, and the switch drawn here is composed of three basic parts. We have the ingress portion, receiving packets from the MAC layer, doing all the ingress processing, the lookups, and taking all the decision about where to route the packet and what modification needs to be applied to that packet. Then we have a TM that stores the packet in queues and then apply QoS policies to decide which queues will go before other queues, etc. And maybe shape the traffic, limit it, etc. And the final part is the egress that is connected to the output port and is doing all the packet modifications before we send out the packets. So this is a simple or a basic switch, and we will evolve it into a VOQ system. So the first of only two steps is to introduce what we call the fabric. And the way to think about it is just a dumb connectivity medium between the TM stage and the egress stage. So no need to take any assumption about the fabric architecture or the characteristics, just a dumb connectivity between the ingress and the egress. And by doing so, what happened basically is that the queues are becoming virtual output queues. Why there are virtual output queues? So if you think about it, the queue, all the essence of the queue, all its properties and association is to the egress port, but it resides together with the ingress portion. So it's not an output queue because it's not part of the output stage. Therefore, it is a virtual output queue. Okay, so this is the first step we are doing. And the second and actually final step of becoming a VOQ system is to introduce more devices and create a bigger system. Now, the fabric in that case is again the same DAM connectivity, a full mesh connecting every ingress to every egress. Now, one thing to note about this drawing is that we draw what we call an unfolded view of the device. So if you look on the top row, you will see ingress A and TMA on one side, on the left, and then egress A. In reality, this is the same silicon, the same die. But here we draw it as two different devices. But again, in reality, they are the same device, device A. Likewise, device B is drawn as two devices and device C is drawn in two devices. And what makes it a VOQ system is that if you have noticed, the number of queues now is much bigger than before. In the previous slide, we had queues only to the local ports because it was a single device. And in a VOQ system, you have queues to each and every output in the system. So every traffic management stage is maintaining queues for each and every output in the system. This is what makes it a VOQ system. And although this system is composed of multiple devices, it behaves as a single hop switch in the sense that every packet received on a given input will do only one ingress processing, will be stored, will be queued in only one queue towards its destination, will cross the fabric to the destination device, and then only once will cross the egress device. So no matter what is the input and the output, every packet is subject to ingress, TM, egress. So in that sense, all the packets experience a single hop behavior of the system. So now that we understand the essence of a VOQ system, another level of details may be to explain the efficiency and the benefits of such system. And to do that, we need to understand the scheduling that is happening. So what you see on this drawing is a single output, and on the top, and on the bottom, you see all the input devices, all the VOQs that points to that destination device. And you see two types of connections between the devices. The blue lines represent the real traffic, packets being sent from the ingress to the egress. And the red lines represent control messages being passed from the egress to the ingress and from the ingress to the egress in both ways. So what we have is on each and every egress device, we have an egress credit scheduler, and it maintains a dynamic database of all the queues that points to that destination, and it maintains the status, meaning how much traffic, how many packets are currently pointing to that output. So upon receiving a packet and storing the packet in any one of the VOQs, a status message is sent to the respective credit scheduler. For every VOQ, there is one and only one credit scheduler. This credit scheduler will update its dynamic database representing all the traffic. and it constantly allocating credits according to the actual port rate to all the requesting queues. So the credit scheduler is aware of the actual current capability of the port to send traffic. So if this is a 100 gig port, for example, and there is no flow control, then it will generate credits in a rate of 100 gig. If it's flow controlled or you want to shape the traffic to another bandwidth, then it will generate credit according to the constraint that you apply. And after generating the basic credit, it distribute or allocate the credit to all the requesting VOQs according to the QoS scheme between the requesting VOQs. So for example, higher priority queues before lower priority queues. Some queues may be shaped to a given rate. So after you allocate that amount of traffic, you will move to another VOQ and so on and so forth. So in very short, to view the advantages of such a mechanism, so it provides a natural isolation of flows, preventing one flow to block another flow, to do what we call head of line blocking. And this is what we call a pull strategy versus the typical push strategy that is used by simple or basic switches that pushes the traffic towards the destination, regardless if that destination is oversubscribed, cannot send the traffic out because it is flow controlled or blocked or for any other reason. And by doing so, we prevent packet drops and we prevent blocking of one flow blocking the other. So after we have basic understanding of VOQ system, let's see what needs to be done in SAI to support that. So of course, we start with the basic SAI that is already implemented for basic switches. And in essence, we needed to add only one object, which is the system port. So as you can see in the drawing, if you look on device A, for example, it will send, device A can send traffic to all the system, to all the ports in the system. Therefore, we need an object to represent each and every port in the system. And actually, when you look on the SAI data plane functionality, you will see that it mainly affects one function in the data plane, which is the forwarding databases. So the forwarding databases needs to use this new SAI concept, the system port, because any given packet, according, of course, to the packet address to the addresses in the packet may be sent to any one of the ports in the system. Therefore, we need the system port to be able to direct the traffic to any port in the system. Again, this is a single hop system, meaning that the decision taken by the ingress device applies to any port in the system, any system port. So this is the system port, and it is used mainly in the forwarding layer, in the forwarding function. All other functions keep the same SAI functionality. So if you think about VLAN membership, spanning tree, router interface assignment, they are typically associated with the local ports, not with the system port. Another addition to the SAI, which again is not mandatory, but it contributes the efficiency of the system, is that in such a distributed data plane, it is best to modify the packet and maintain all the packet editing databases only on the egress device. Alternatively, of course, you can the user can store all the, let's say, tunnel information and all the encapsulation information and at each and every device. But this is a waste of information and makes the management much more, heavier and complex. Alternatively, each SAI image, for example, device A is managing the databases for the tunnels and the encapsulation that is sent out through device A, and provide a handle, a pointer to other SAI images to use. So when they send traffic to a tunnel that resides or going out through device A, they will use that handle, that pointer, instead of maintaining the actual tunnel database or encapsulation database. So these are the two main changes for SAI to support the VOQ system. Finally, a short State of the Union. So we approved the required changes for VOQ system on Q2 2020. This is done, check mark. And Broadcom delivered first VOQ system SAI in version 1.63 code drop, check mark. Nowadays, Broadcom releases support for Jericho 2 SAI. So this is happening these days. And looking forward, in Q1 2021, we will provide SAI support for Jericho 2 C++. So thank you. Sorry for the blitz presentation, but I had 15 minutes and I almost did it in 15 minutes. So to you, Esfaran.